Thanks for the introduction. Let's say we'll continue a bit on the topic that was already introduced by Simone. So this presentation will be about the feasibility region and the exploration of the effect of lesser process parameters on the mechanical properties, in particular fatigue performances of aluminum alloy AM205. What we'll see brief presentation of the powder that we used, the exploration of the theoretically lesser powder bed feasibility region that we can predict on the basis of an analytical model that we introduced some years ago, some microstructural investigation to understand what happens to the material when we vary the L-PBF process parameters, the investigation on what happened to the rough surface of our samples, and so surface roughness analysis, investigation on static mechanical properties and high cycle fatigue performances that we are printing. This work is still an ongoing experimental campaign, so I'll show you today some preliminary results, and we are still working and still finishing to investigate the additional effect that I'm showing you this morning. So, passing to the powder is AM A205 or A20X powder that is aluminum alloy, a series 2 aluminum alloy. So an aluminum alloy that is based on the copper aluminum intermetallic compound, the well-known theta prime phase. So it's an aluminum alloy that works as a precipitation hardened aluminum alloy of the standard family, but due to increasing its printability and so reducing its tendency to produce hot cracks that are the problem of printing aluminum alloys with L-PBF, but also as welding as well known, it used titanium diboride that acts as grain refiner because it cannot be melted by the temperature that we can reach in our molten pool. And so we have already some solid material that acts as grain refiner, and in this way, we can avoid the occurrence of hot cracks. And so it allows to use this powder for a very wide feasibility region because we can explore different process parameters, paying attention only on the quality of the material in terms of density, pores, standard defects introduced by the L-PBF process, but not dealing with the need of avoiding hot cracks because it's a material that has a very low tendency to produce hot cracks. Also, in this case, the material uses also silver and magnesium as for the omega phase, so for introducing an additional precipitation hardening and strengthening mechanism. In this way, this material is gathering more and more attention in the field of L-PBF, of aluminum alloys, and lightweight structure due to its very interesting fatigue performances, both at room temperature and at a high temperature. The powder that we are using is a standard powder that can be used for L-PBF, so a powder having a PSD with a central value about around 39 microns, with the extremes, the 10 and the 90, between 18 and 60 microns. It's a good powder distribution for printing with a layer thickness of 40 microns. That is the one that we adopted in this phase of the process. All the samples were printed with the Renish M 500S Flex L-PBF printer that we have in our laboratory in Pisa. All the samples were printed in vertical direction, so having the loading direction of the tensile and fatigue samples aligned with the build direction, the direction of motion of the build plate in the machine. We investigated different set of process parameters. So here you can have an example. Surface condition only as built conditions, so samples were not machined because we want to deal with the effect of surface roughness on the effect on the fatigue performances of our material. In terms of heat treatment, today I'll show you only the data about the as-built material. That is the first phase that we explored. The heat treatment that is based on T6, standard T6 heat treatment for aluminum alloy is still in an ongoing experimental campaign. We printed the samples and we are quite ready to test them. So how we can define the L-PBF process parameters? We used an approach that is derived from a previous work that we published some years ago. It's based on a Rosenthal solution for modeling the thermal field produced by our laser powder source. So it's a very simple model that introduces some very significant hypotheses and assumptions, in particular the fact that we have a pointed source moving at constant velocity, so we are dealing only with a process in a steady state. It needs that we have to be far from the boundaries, but it's a very simple model that allows to predict very easily and analytically what happens to our process, and so it allows to define the L-PBF process parameters, at least for the first definition for experimental campaign, in a very easy and efficient way. What we can obtain with this model is a prediction of the radius and the aspect ratio of our melt pool, so the width and the length of the melt pool. Based on that, we can have a prediction of the occurrence of lack of fusion, based on the fact that we need to have at least a mortar pool radius that have to match the minimum dimension based on the layer thickness and that distance that we are using. This model was validated in the past on Inconel 718 alloy and on different material on the basis of literature data, on Inconel 718 on the basis of experimental data that carried out in test. Based on this model, I started defining a wide set of L-PBF process parameters, up to now keeping a constant layer thickness up to at 40 microns and a constant H distance at 100 microns. And so I varied to now only the power and the velocity. Here you can see all the square on our feasibility region that represent the different points and different conditions that we explored. On this feasibility region, you can see a gray area in the bottom below this line that is our prediction of the lack of fusion occurrence. In this area is where the model predicts a not safe condition, predicts the occurrence of lack of fusions, while on the top, this line, we have safe from this phenomenon. It's clear that for using a model like this, we need to have an idea of what is the real power absorbed by material, and so knowledge of the laser absorptivity of our powder, and the need of using this shape and this allocation of the experimental points for our experimental investigation. It's also that we need to have a better idea about the powder laser absorptivity, and so we get an idea of what is the effective powder, because in the model we introduce the effective powder absorbed by material. Let's pass through first experimental evidences. We can see that the point that belongs to a region below the lack of fusion boundary features the standard defects that can occur when we have a lack of fusion, and not huge lack of fusion, but the occurrence of some sporadic lack of fusion phenomena, as predicted by the model. When we are far above our region, so at higher powder, but the relatively low velocities, we have the occurrence of keyhole. That is, as you can see from this huge number of white round pores that are typical of keyhole in L-PBF process. While if we are in a region that is above the lack of fusion, but at power that are not extremely high, we can produce a very good dense material with an average density of 99.97%, with very regular, let's say, melt pool tracks, as you can see from the image where you have the material etched with color etchant. And then you can see all the traces of the precipitation that occur on melt pool boundaries. And so you can see how the process is most stable. If we increase the velocity and keep being in our safe region, the density keeps being very, very good. You can see that the dimension of the molten pool is increased. The process is less stable, but still produce a very good density. When we increase a lot the velocity and the powder, what starts occurring is humping phenomena. So local instabilities of the molten pool that can create some seldom randomly occurring pores due to instabilities occurring because we are increasing a lot the aspect ratio of our molten pool. On the basis of that, for these preliminary investigations, we selected two experimental points after this metallographic investigation, two cases for static mechanical tensile testing and fatigue testing. So A set and B set. A set is a set that can produce a very full dense material. B set is one in the, let's say, region where humping phenomena can occur, but with B set we can double the process productivity. So it's going to be very interesting on the also on the industry point of view because it solves one of the problem of the intrinsic problem of the process. But we see we increase a lot also the material defects. So surface roughness, we measured the surface roughness with a standard profilometer in different position around the circumference of our samples for fatigue and testing. You can see that the surface roughness is almost constant while we rotate the sample. One of the advantage of using round samples that with this powder have quite no effect of the orientation of the sample with respect to the recoater orientation. But passing from A set to B set, we have more than double the roughness. The roughness is increased of 140%. So the surface roughness increased a lot, both in terms of average roughness, total roughness, and depth of the surface roughness values. We have a quite huge increase in surface roughness. If we see what happens in terms of tensile properties, here the data about the A set are more or less in line with what you can find in the literature in terms of strength, elongation at fracture, that even bigger, a bit higher than what was suggested by the powder manufacturer. When we pass to the B set, we see that material features have lower yield strength and a very lower, significantly lower elongation at fracture. We see what happened in terms of fracture surface. We see that for the A set, the material presents almost no necking, but and a surface that with some sporadic pores, but full dense material as we expected. In the case of the B process parameters, the surface fracture is perfectly orthogonal to loading direction, and the surface features a quite huge quantity of pores. This is also in particular because when we deal with elongation at fracture and tensile test, a surface and a region of the specimen that is full of pores will be for sure the section, the surface where the defect localization occurs, and tensile testing expose the worst region of the sample in terms of internal pores that has like already present dimples, and so it affects significantly the elongation at fracture as it happens also with different materials. So here also I'm showing you the worst condition among the various curves of the B process parameter set that we explored, but for a work like this, for us, what's most important to understand how the B process parameter set decreases the strength of the material. So we are dealing with what happened in the worst condition among the samples that we produced. If we pass to see what happens to fatigue testing, we carried out fatigue testing with a load ratio of -1, so fully reversed load, on a Romulo resonant machine using a load cell of 5 kilonewtons. Round samples with a diameter of 6 millimeters. Here you can see on the full black triangles the result of the A set, while in the hollow triangles the result of the B set. We can see that the result of the A set are more or less in line with the results found in the very recent literature about this alloy. When we pass to the B set, we have a decrease in fatigue strength, a decrease of about 30% if we consider the fitting point at 1 million cycles. So a decrease that is significant, but much lower than what we experience in the tensile testing and in surface roughness increase. We see what happened to the fitting lines we can obtain on this preliminary data that we have. The two process parameter set doesn't affect so much the slope of the two curves. We have just a translation. The slope tends a bit to have a standard convergence when we reduce the fatigue life, as it's typical, while the two curves are a bit more separated when we go to lower stress and to higher fatigue cycles, as is typical due to the effect of surface roughness. Just to conclude, the fractographic analysis, what happened to our specimen? What is the killer defect? For the A set, the killer defect, as you can see here, was on the surface roughness. The crack originated from the surface and propagated in the sample from surface roughness valleys, more or less. So valleys both in circumferential direction and the longitudinal direction. And also when we have some subsurface pores, the fracture started from the surface roughness values. For sure, surface roughness values that were near to subsurface pores that increase a bit the stress in that region. If we look in detail what happened to fatigue crack propagation, we can see that the material have no significant delamination, no melt-pool delamination, but in some cases we have some jumps between different planes due to some delamination around some molten pool geometries. It's something that seldom occurs, but sometimes we can observe that also the melt pool boundaries can become some weak points, but only in the final part of, say, middle part of fatigue crack propagation. What happens in terms of the B process parameter set? B process parameter set, the crack onset was on the surface. As for the A set, in region where we have surface roughness valleys or surface roughness defects, because we have some defects that are very deep valleys that occur due to some local melt pool instability that occurred here on the surface of the sample, and also some bigger pores that occur nearby the surface of our sample. So they act as killer defects and are much more severe than what happens in the A set. And also, if we see what happens in terms of fatigue crack propagation, in this case, the material, due to its lower density, shows significant pores, round pores, but also pores that are more elongated and then go across different layers that are the typical pores that occur due to melt pool instabilities and humping phenomena. So just to conclude, we saw a preliminary validation of the analytical L-PBF feasible region for this alloy, for the AM205 minimal alloy, passing from two different sets of process parameters, one stable set and another one that is more oriented to productivity. We had a significant increase in the surface roughness that was increased by 140%, so very huge increase in surface roughness. The fatigue strength was significantly reduced, in a ratio that is much lower than what happened in terms of surface roughness, even if surface roughness is the killer defect. So the strength reduction at 1 million cycle is about 28%. Fatigue cracks, as I showed you, started from surface roughness valleys and surface roughness defects, while the elongation at fracture was significantly affected and even more affected than the fatigue strength. Based on this, in the future, we'll start rationalizing the data on the basis of approach based on fracture mechanic approach, like the Murakami approach, dealing with surface roughness defects and considering them as the origin of our fatigue performance of the material. And so, thank you for your attention.